some guy from Berkeley. 네, 이거 올려놨나? Right? So I just wanted to use this as a supplementary. This is a slide from Berkeley, UC Berkeley. I just downloaded it, maybe just wanted to look at it. For operating system course, this is not for the introduction to computer science. 이 슬라이드는 그거 아니에요. 그 전산학개론에서 쓰는 슬라이드는 아니고 오퍼레이팅 시스템 운영체제 하는 첫 번째 뭐 강의 자료 정도 되는 것 같은데 거 아니고 다른 사람 거 잘 만든 거 있길래 한번 가져와 봤어요. Hopefully it has more details on what we try to discuss. We have seen this type of architectures already, so it's all the resources, computer system architectures that we do understand how they work. Bus. So, 아이고 이거는 애니메이션이네. So goal of the operating systems. 미안. Goal of the operating system is operating system is one of the big part of the system software. It is a simplified execution of the user program, make solving user problem easier. What you're using on top of the operating system is a user software, user programs. Using computer efficiently, we have seen that statement many times in your textbook as well. Allow sharing of the hardware software resources. Make application software portable and versatile, blah, blah, blah. Provide isolation, security, protection among user programs. These also mostly security features of it. When programs are made into object files, loaded into a memory, one of the key features of the operating systems must be doing is protect its memory space. So I usually have multiple programs running in my system, right? And they're somewhere in the memory. They all put together. Make sure no process can touch someone else's memory space. 이렇게 일반적으로 이렇게 메모리 그리라면 이렇게 그려요. Typically, they use a lot of blocks like this. Memory from memory address. They usually draw this way. OS, usually first part of the memory. So we can boot the system. And maybe program one, process, is here. Process could be anything, your Microsoft Office or smaller programs that you can use. Process 2. They usually draw it this way. It's more of a logical view of how your program, how your memory look like. And then each have their address. This is a starting location of a process 1, and they end at this location. So this is given only to process 1. So one of the programs. This is only given to process 2. This is how they, to describe the memory usage. This is what's happening actually. But they say provide isolation, security. What usually hackers or some programming people try to do is maybe some process of P2 try to access to space of a P1. Usually this is not allowed. So this is a protection of your memory space. If something like this you allow to happening without any regulations, then most likely your system will behave in some awkward ways. 이상하게 행동하고 갑자기. That's what usually hackers try to do. So if you define a list, maybe your list is somewhere around here. 0, 1, 2, 3, 4, right? Sometimes you forgot how many things were in your list, arrays, and you wanted to pointing to an array that doesn't exist. Maybe 0, 1, 2, 3, 4, 5. But you forgot. You thought there is a 6th one, like this. But that's actually not there. But in your program, you try to access this space, which doesn't exist. So this may be pointing, if you're lucky, you're pointing somewhere around here, or it could pointing anywhere like this. Problem. Usually program crash. Or if that happens, hackers, they try to do this intentionally. and then goes to a administrator mode. 이렇게 하다가 재수 좋으면 뚝 떨어진다 그래갖고 갑자기 관리자 모드로 뚝 떨어지는 경우가 있어요. So it's a protection of your memory space. It's a very important part of your programming. That's what operating system also try to protect. The OS controls this memory access. They also try to give this memory access to certain programs and take it back. What if program 2 finish? What if the program 2 finish? Or you kill the program? This is become empty again. OS take it back and bring it, they mark it as a free space. And hoping for the next program start, we're gonna give that space to the next program. That's what OS try to do. And OS wanted to nicely organize this memory space. Of course, there are more techniques out there to practice, but that's later. Overall, improve the overall system reliability. Hopefully, when we take in multiple process, multiple memory, multiple programs, hopefully operating system can do this more efficiently without any problems. So they need to keep track of what is a free space, which one is not a free space, stuff like that. This is very nicely drawn. In fact, if I already told you this is memory, right? Actual memory, 진짜 memory는, actual physical memory look like this. Well, I draw it like program 1 all stayed in the same space, right? Actual programming 1 like this. Piece of programming 1 is here, piece of programming 1 is here. They're all separate into pieces. 이렇게 되어 있어요, 실제로. So you need to be pointing to a right location every single time like this. 실제로는. Physically, they store it this way. Logically, we draw this way. So it's much easier to organize. So there is a translation step in the between. That's what operating system is doing most of the time. 중간에 원래 이 주소를 번역해주는 프로그램들이 있어요. 그게 part of the OS. OS is memory management, right? One of the key functionalities that we mentioned was memory management. 이게 살짝 머리 안 와닿으면 그거 생각하면 돼요. 디스크 fragmentation 하는 거 봤어요? One of those Windows functionalities, defragmentation or organize your disk space, right? And then if you click on the program, they look like this. Tiny boxes, red, blue, right? Have you guys done this before? 그 defragmentation, 디스크 정리라는 메뉴 윈도우에 보면 있죠. 이건 물론 메모리 고용의 디스크지만 이렇게 실행하면 막 이런 게 나오고 빨간색, 초록색 막 섞여 있죠. What happens if you finish the disk organization, disk fragmentation? 그럼 나면 어떻게 돼요? 이 그림이 어떻게 생겼어요? 혹시 끝까지 해본 사람 있어요? 오래 걸리죠? 몇 시간씩 걸리죠? 그러면 파란색은 파란색끼리 이렇게 뭉쳐 있고 빨간색은 빨간색끼리 이렇게 뭉쳐 있어요. 나중에 끝나면. They were stored like this before. They wanted to bring it together like this later. Of course, this is a memory. This is a disk, but idea probably similar. Why do you prefer they stay together? In terms of disk, for example, why do you want to? Why are you doing this? What is the purpose of doing a system disk defragmentation? 저거 왜 하지? 가끔씩 윈도우가 하라고 시키죠. Why? We discussed this briefly last time. 왜 하지? 그냥 시키니까 안 와? 몇 시간씩 컴퓨터 켜놓고. 그거 할 때 잘 들어보면 디스크에서 계속 끼익 하는 소리가 몇 시간씩 나요. 소리야? 왜 하지? 이거 왜 하는지 아는 사람? Well, there are many reasons, but mostly you wanted to put a similar data into a closed area so you can read them faster. You can read them faster. Why? What was the problem of the disk architecture? Tracks, record, there is a moving arm moving in and out, right? They also discussed about the latency. Latency, right? We discussed it. Maybe if we put a similar stuff nearby, maybe latency will be faster. Less arm movement. So from time to time they ask you to do this. 그냥 놔두면 그대로 그냥 쓰면 계속 지저분하게 다 쓰니까 여기 쓰고 저기 쓰고 여기 쓰고 저기 쓰고. But usually you don't experience that improvements even after you do that fragmentation. fragmentation 하고 나서 컴퓨터가 갑자기 빨라져요? 그렇진 않죠. 그렇죠? So that's what they say, actually meaning a lot of things. It's a very summary of page. So actually in the operating system course, each one is a single topic. Single topic. Why should I study operating systems? Why? You should just why you need to understand some of the operations for the in the operating system. Need to understand interaction between hardware and applications. Blah blah blah. Needs to understand the basic principle of design of a computer system. What we want to do, we wanted to use CPU and memory efficiently, right? What are the algorithms being implemented in order to achieve that goal? So let's try the very basic basics like these. Increasing the need for specialized operating systems, many different operating systems, embedded operating systems, real-time operating systems like aircraft control and blah blah blah. It will come up in the later slide too. 근데 embedded, I'm not in the field for embedded operating systems, but 뭘까? Embedded operating systems. Perhaps a bit smaller, but it's much close to the hardware development. Embedded. The Windows is not a embedded software. 좀 작은 디바이스에 들어가고 좀 사이즈가 작은 operating system. 이렇게 지금까지는 그렇게 봐도 될 것 같아요. So these are the systems like today. Some examples. 그죠? 아이고. 뭐 많네. This is the one country you should never have a war with. 미군 애들 맨날 들고 다니는 장비. Everything is the operating system on top of these devices probably embedded operating systems. This is what the computing center looked like actually. 들어가면 it's very noisy. A couple of days ago there was a fire at the Samsung SDS card. They have a fire in these rooms. 전체 들어오면 되게 시끄러워요. It's very noisy. And they usually have a special type of fire extinguisher. It means that if fire happens, you cannot put water. 물 뿌리면 안 되잖아. It's all machines, right? Computers. So they actually put a CO2. They close the room, CO2. So if you stay inside this room when fire happens, then you will die because you cannot breathe. 들어가면 방 CO2를 불나면 물을 못 뿌리니까 CO2를 쫙 방을 닫고 뿌리면 되죠. 이런 데 있는 컴퓨터들이나 네트워크 장비들은 쉽게 끄지도 못해요. 끄는 순서가 다 정해져 있어요. 그거대로 안 끄면 나중에 다시 켜지지가 않아요. 근데 뭐 귀찮으면 그냥 다 전원 내리고 도망가는 거죠. A lot of devices 이런 거 있으면 참 좋겠죠. Like the ferry incidents. 요즘에 여객선 그거 때문에 참 말 많은데 저런 디바이스들도 있으면 참 좋겠죠. 요즘엔 더 많잖아. Wearable devices like these ones. So there are many different systems out there. It's more of a common use today. Anybody has a car? 자동차 있는 사람. 자가용 있는 사람 아직 없지. OnStar or Hyundai, Kia, they also have their own systems. 가끔가다 if you see movies, they usually have a special system that you push somewhere in the car, then you can talk to the operator. And then they can start your car and call 911 and stuff like that. OnStar is also part of the big system that running maybe big operating systems. OnStar나 뭐 기아, 현대 건 이름이 뭐더라? 뭐 가끔 영화 보면 긴급 상황에 이렇게 버튼 뚝 누르면 자동차 시동도 원격으로 켜지고 그런 거 있잖아요. 영화 안 봐? 영화에 그런 거 나와요, 안 나와요? 나오죠. 그 뭐 다 조금 비싼 차 옵션 하면 다 있는 옵션이니까. 그죠? It's also a big part of the system. Also navigation. 혹시 현대차 부모님이 현대차 뭐 내비게이션 있는 사람 있어요? 한 달에 얼마씩 내면 내비게이션에서 그 지도 자동으로 찍어주는 사람하고 통화가 가능해요. 이름 잊어버렸다. 뭔지. 이렇게 길 못 찾겠으면 찍기 귀찮으면 그렇게 버튼 꾹 누르고 내 갈 장소 알려주면 그 사람이 대신 내 내비에 찍어줘요. 그런 거 비슷한 거. Traffic control systems and smart grid. 이것도 also part of the big systems they discuss. Smart grid? 난 잘 몰라. What is a smart grid? 스마트 그리드가 뭐지? 뭐 전력 시장 어쩌고. 그래. 면접 그래갖고 참 잘 보겠다, 그죠? 뭐 전력 주고받고 하는 시스템으로도 관리하고 막 이런 거잖아. 옛날에 전력이 한쪽에서만 한쪽으로 가는 구조였다가 이제는 여러 사람한테 원할 때 한쪽으로 보내준다던가 이런 길을 터주고 하는 게 많이 변했죠, 그죠? 그건 뭐 쓸데없는 얘기니까 그건 뭐 중요한 건 아니고. So hardware complexity increases. Moore's law, transistor and chip every 1.5 years. I think it twice. They usually discuss for the memory part, right? What you can store in the same space every 1.5 years, that's 18 months. What you can store in that same space will double, right? That's what it means. What does that mean? What does that mean? Same space doubles. It means you can put more transistors in the same space in every 18 months, twice. 그 이상한 것도 있었죠. 무슨 황슬러 해갖고. 혹시 들어본 사람 있어요? 그 지금 누구지? 그 KT 회장님이 황창규 회장님이죠. 그분이 황슬러예요. 황슬러. When he was head of the Samsung memory, then he went to some big conference and then 얼마였더라? I think faster, 3 times better, 3 times within 2 years or something. So he said, my law, 황's law. 해갖고 저거 Moore's law를 뛰어넘는다고 막 3배, 20개월에 3배가 된다나 뭐 하여튼 뭐 그런 얘기가 있었어요. 근데 한 몇 년 있다가 금방 깨졌죠. 안 돼가지고. 아래 있던 직원들이 얼마나 고생을 했겠어요. 그 맞추느라 회장님이 가서 말씀을 하셨는데 기술은 안 나오니 얼마나 힘들었겠어요. All they try to say is the hardware increased fast, especially those memory spaces. You can put more transistors and tiny devices in a smaller space. That's how much it increased. It's increasing really fast. As well as the software complexity increases. It's a slide from other courses. It says the number of code, here is number of source code, number of lines in the source code. Typical question, interview situation questions. I don't know they still ask you this in the interviews, but when I were you guys like, just about to graduate, the common questions companies ask for the interviewees were, what's the maximum line of code you have ever wrote? 총 지금까지 몇 줄이나 코드를 작성해 본 것 같아. 이런 질문이 참 많았어요. What if I ask you now? What is the total number of code that you have wrote before? 뭐 머릿속으로 막 계산하죠. 몇 줄이나 되나? 지금 몇 줄이나 될까? 다 합쳐 가지고 500줄? 이제 막 시작이니까, 그죠? They usually, for a single project, how many lines of code? People usually say, a couple of thousand. Some people say 10,000. Might be lie. 생각보다 자기가 직접 짜는 거 그렇게 많지 않을 수도 있어요. Anyway, so well, it doesn't mean that number of lines of code reflect the complexity of the software, but in terms of quantity, it might be a measure to look at. So this is total line number of codes for each some systems they wanted to compare. So first thing was what? NASA space shuttle control. So the operating system they wanted to build for the NASA's space control space shuttles was, I guess, above 1 million lines of code. 1 million lines of code, which is 80s, 그죠? 저 정도면 80s, 1980s, 80s. When Windows 3.1, first version of Windows in 1992, it was having a bit more than that, I guess close to 2-3 million lines of code. NT, 1992, is server version of Windows. More, now it's close to 5 million lines of code. 와, Solaris 본 사람? Anybody looked at Solaris? Solaris is also another type of operating system for servers, more common for the servers and stuff. 이것도 it's close to now 10 million, 9, 8 million. Windows 95 goes to what? 이거 얼마야? 15 million. 15 million이면 얼마야? 1,500만 줄이죠. 1,500만 줄 of code. Windows 95, 98, almost going up to 20 million lines of code. Windows NT next version, 20 hits. Red Hat Linux, also very popular user ones in 2000s. Close to 20 million. Red Hat next version, 30 million. XP. XP goes to, compared to Windows 95, more than a double. 40 million lines, 4천만 줄 코드가 4천만 줄. Can you understand 40 million line of code? If it go over 4,000 lines of code, it would probably be difficult to understand anyways. 그죠? XP 40,000, Vista 50,000. Well, even if you don't understand how many lines, if you don't know the exact number of millions lines of code, you can just compare the size of these CDs that you can purchase. 그렇죠? Windows XP만 해도 maybe less than 600 megabytes of the OS. 그 Windows 8, 7, 3.2 gig DVD. So software complexity is very, very increasing fast as well. Also very difficult to understand which part is which. That's why you experience so much update. 업데이트 되게 많죠? 윈도우즈 업데이트. 저렇게 라인이 많으니 버그가 있을 수밖에 없겠죠. 그죠? So sometimes software is referring to it's more important for organization. Architecture, who's developing what, you wanted to manage between many hundred thousands of programmers to work for the single project to run. We all know this. 아이고. So we all know this now. We have looked at this: hardware, operating systems, application programs, users. That's what it takes to run a computer too, right? It's another way of saying it. It's okay. So operating system key features, again, resource allocator. To allocate the resources, memory, software, hardware, everything, we treat them as a resource to a program and system, and OS will manage them efficiently. So make sure there is no memory leakage. 메모리 리키지 하면 뭘까? 메모리 리키지. Memory leaks. Why you have a sometimes blue screen in some cases, well, old Windows systems. Well, sometimes when your program is doing something, maybe you declare a array. Array 이렇게 딱 선언하잖아. It means that you will have a space somewhere in the memory in my array. Okay. And your program maybe have a for loop. You keep running and running again, allocate the array every single time. Maybe if you forgot to delete it. In C, usually if you allocate the memory space, you have to delete it after you finish. 그죠? You forgot to delete the space. You will fill up the memory with your empty array over and over again. After a certain point, your memory will be full. Operating system doesn't know what to do because there is no empty space. They usually give you warning message that you're running out of memory. Or what might be the best way of solving the situation? Reboot, maybe. So this is a common mistake that people like us, who's just beginner programmer, usually we're not very careful with this, deleting this memory spaces. And this is going to be a memory leak. 메모리가 샌다고 얘기하죠. 메모리가 계속 쌓이는 거예요. This is more a common problem in C and C++. And Java might be slightly different. Maybe one of the major difference between Java and C is this. You are responsible for maintaining the memory space in your program. Java, you don't have to. Java will do a garbage collection. Java will destroy it for you. You can declare, but program language itself will kill it for you. 자바로 비슷한 걸 짜면 자바는 안 죽여줘도 지가 프로그램 끝나면 이거 죽여줘요. 그럼 메모리 리기 상대적으로 가능성이 적겠죠? 그죠? Okay, so OS is also a control programs. It's a resource allocator, also a control program. Controls the execution of the user program and operation of I/O devices. Your program running when OS will do a control. This time is for your keyboard input. So you give a CPU time for you transfer the data from your keyboard to the memory, and then you bring it back to your program again. So OS also give an order which one should be doing first. So it's a control software. Conner is a program that executes forever. Everything else is application with respect to the conner. You can think of it as, in the actual operating system, there are two different modes, usually called as a user mode and conner mode. User mode and conner mode. What you are doing mostly, running your program and declare memories that you need, is happening in the user mode. You guys usually play on the user mode. There is a conner mode that is strictly depends on the operating systems. So that part is hidden from you usually. So it's a system part of the software. OS는 일반적으로 커널 모드, 유저 모드 이렇게 나눠요. 그래서 일반적으로 커널 모드는 완전 OS가 자기가 알아서 하는 쪽이기 때문에 우리 같은 일반 유저들은 아래에서 뭘 하는지 알 필요는 없어요. 여러분들이 대부분 하는 건 유저 모드예요. So everything else outside the user space you can think of as a corner mode. That's okay at this point. So they just wanted to bring it down. Log people per computer now year. 그죠? What you need for the computer, big computer need a lot of people now. It's a number are just very smaller to run a single system. Number crunching, data storage, yes. And data processing. It's still a job title as a data processor. 그럼 뭐 하는 거예요? Data processing jobs. Has anybody heard of that job title? Data processing job. 그거 sounds very fancy, but it's simply as you look at the paper, you try to type in into the computer. Put that information into a DB database or system itself. 데이터 프로세서라는 잡 아직도 있는데 아주 되게 팬시해 보이지만 실제로 하는 일은 종이에 보고 종이에 있는 거 컴퓨터로 옮겨 적는 잡이에요. 그런 거 할 때는 아직 still you need a lot of people to work on it, right? But the streaming information from physical world, but current states only a very small number of people is required to run a computing systems. That's it. In 1950s, bare machines, naked machines, as we refer into our textbook, it was hardware very expensive, human or cheap. This was a situation in the naked machines. Structure, large machines run from a console. It's a simple monitor and keyboard. Single user systems, programmer user as an operator. Paper type and punch card. 전에 I show you one of those punch card. 구멍 실제로 뚫어가고 you'd indicate a number and then you put a hole into a punch card. Your program is written on top with a punch card, and in these systems, only one person at a time. They put that as an input to the system, and then they work. It's a very old system. This time, expensive. The hardware itself, the machine itself was expensive and taking a lot of energy as well. Huge as well. I used to. 네, 얘기하지 않았나? My first year. My university, there was a room called Red Room, almost size of the entire first floor in this building. 이 빌딩, IT 빌딩 1층만 했어요. 방 하나가. Computer was there. Very old computer was there. 내가 한 1학년 지나고 나니까 그 방을 비워갖고 딴 거를 하긴 했지만. All these softwares, assembler, compilers, linker loaders, device driver, libraries, common subroutines, blah, blah, blah. Secure execution, because only one program, even only one operator at a time, only one person has an access to that computer, the others must be wait. So in this type of computing room, there used to be a scheduling form outside the room. You have to go from 9 a.m. to 10 p.m. I'm gonna use it, John. 10, 11, someone else. 그렇게 적어놓기도 했었어요. Because only one at a time. Inefficient use of expensive resources. Low CPU utilization, high setup time. I mean, imagine that you try to do your program on the punch card. You put holes in the paper. The last step, you made a mistake. You put a hole in somewhere else. You have to do it again. 그죠? 미치는 거지. 제대로 하고 있는지 안 하는지도 모르고. So that's a naked machine pictures. Some batch systems later. 이게 더 가깝겠다. It's now you can actually give a command to those naked machines. So it's a bit easier to run those programs now. 이것도 뭐 굳이 뭐 대충 설명한 것 같다. That's okay. We're more interested in this part. Supervisor operation controls. Secure monitor that controls the job processing. There is now a mechanism called monitor to control multiple jobs at the same time. Which one is taking where? We can suspend one of the programs running. We can bring it back. Other programs waiting. So we can do a switching between. It also separates the user from the computer. Blah, blah, blah. It's not that. But what was the problem of this approach was turnaround time is even 2 days. Turnaround time is something called as you start your program. How long does it take that program ends? That is a turnaround time. It says turnaround time of a single process takes 2 days. 이틀 걸려서 프로그램이 끝났다는 얘기예요. 프로그램 돌아가는 게. And also low CPU utilization. I/O CPU could not be overlapped. So there wasn't a perfect control between switching between I/O operation and CPU operations. So that's why they had to wait a lot of time to finish something up. So old-time systems. 이것도 지나갈게요. I just wanted to take a look for other type of slide for that I/O completion. 이것도 조금 그렇다. 넘어가자. Maybe I can discuss for the multi-programming. Multi-programming means, like we discussed, many programs stays in the memory at the same time. That's a multi-programming environment. That's what we have now. So use something called interrupt to run multiple programs simultaneously. Simultaneously means it looks like working at the same time. When a program performs I/O, instead of polling, execute another program till interrupt is received. So if one program is getting a data from DVD drive, that's I/O, input and output operation. And because that operation doesn't take a CPU time, so I'm gonna give a CPU to some other program is waiting. So when it's done, I'm gonna let them know, interrupt, just saying, I'm done. Give a signal to each other. So I/O is done. When I/O is done, the program that was doing I/O operation would tell the operating system, I'm done getting the data from DVD drive. Give me my CPU, something like that. So it's more, that's called an interrupt-based system. So operating system is usually called as an interrupt-driven system. Every process will call up an interrupt to do something else, especially switching between different process to switching in order to get CPU time. So it needs a multi-programming, requires secure memory I/O for each program, requires intervention if program loops indefinitely. What if your program has a infinite loop? Let's say your pseudocode, your algorithm you made some mistake, or even in your program you made the mistake that your loop never ends. We discussed such cases, right? Then what can you do? What is usually happening? It seems stuck in the memory, it's doing whatever it's doing over and over again, right? It simply say operating systems, in order to do a multi-program, there must be some type of stopping mechanism if one of the processes in the infinite loop. Maybe something like, it's also like timer like. Maybe if I'm waiting for some process, if I give a CPU time to a certain process, it doesn't give me back to control within maybe 10 minutes, I kill them to check, assuming that they are in the infinite loop situations. OS must be able to check such situations. Otherwise, 계속 기다려야 되니까. Otherwise, you're stuck forever. So, require CPU scheduling choose the next job to run, because only one process at a time for CPU, but you have multiple programs are waiting for CPU. So OS must select which process to do first. It has a lot of issues too. There are algorithms required to choose which process to be executed next. So what do you want from your operating systems when you're using your computer? 일반적으로 컴퓨터 쓰면 뭘 원해요? Usually, I don't want to wait. Hopefully, if I start some program that finish soon. It's like, in order to do that, I need to use my CPU a lot. So it's OS goal is for maximizing CPU utilization, and you also wanted to minimizing waiting time. Minimizing, for example, turnaround time that I mentioned. Turnaround time, again, the time it starts with the process, time it ends. So hopefully my operating system is nicely written to minimize turnaround time while maximizing CPU utilization. So it has two goals. One maximization problem and one minimization problem, which is, it has pros and cons. It's a trade-off between the two. 나중에 OS 하면 CPU 스케줄링 알고리즘 나오는데 뭐 어떻게 보면 되게 간단해요. 뭐가 있을까? 프로그램 1이 뭐 한 10초 걸려 끝나는데 프로그램 2가 한 5초 걸려요. 프로그램 3가 한 3초 걸려. 근데 갑자기 걔네 셋 다 메모리에 탁 들어왔어. 1, 2, 3. 그러면 10초 걸리는 걸 먼저 할까? 5초 걸리는 걸 먼저 할까? 3초 걸리는 걸 먼저 할까? 정답이 있을까? Depends on what you want. Depends on what you want. What if the process 1, which takes 10 seconds, it's really, really important program? Then you need to do that first, right? Or P1, P2, P3 are all equally important. But I like to maybe minimize the average waiting time for each process. 기다리는 시간 줄이고 싶으면 3초라는 것부터 먼저 하면 3초 하고 5초 하고 뭐 이렇게 하면 나머지 10초 있는 애 먼저 하는 것보다는 나머지 둘이 좀 덜 기다리겠죠. So it depends on what the operating system wants. It depends on the designing issues. You can choose which CPU algorithm to use. 나중에 OS 들으면 나오긴 해요. 뭐 여러 가지 문제도 있겠죠. 뭐가 있을까? 재수 없으면 어떤 프로그램들은 한 번도 CPU한테 못 가는 경우도 있을 수 있잖아. 그죠? 뭐 상황에 따라서. 그럼 어떻게 해? 한 프로그램은 계속 시스템에 돌고 있는데 끝나질 않아. 그럼 그것도 OS가 어떻게든지 해결해 줘야 되죠. 어떻게 해결하면 될까? 우선순위도 하나의 방법입니다. 우선순위를 오래 있던 놈을 우선순위를 올려줘갖고 그 다음에 좀 되게 한다든가. 다 알고리즘이에요. 지금 친구 얘기한 거 다 part of the algorithm. Depends on the situations that you want it to be fair and you want it to achieve what your goals too. So CPU scheduling algorithm is also a very important part of the operating systems in terms of controlling multi-programming environment. Time sharing. At this point, hardware getting cheap, human getting expensive. Why do they say it? Oh well, CPU nowadays cheaper than ever. 그죠? Memory cheaper than ever. 요즘에 뭐 1기가 한 10,000원이나 하나? 9,000원 막 이렇죠. 그죠? So when the system is getting more multi-programmed, more time sharing, is now. I guess 이거 나올 때는 이제 펜티엄 나오고 막 이럴 때, 486 펜티엄 넘어오고 막 이럴 때. Programs are queued for execution in FIFO manner. Programs queued for execution in FIFO manner. FIFO shorting for first in, first out. First program comes into the system will get executed first. But we want it to be fair. Maybe we want to give a chance to every single program that comes in. First one doing something for 10 seconds, 1 second, and then go to next one, another second, next one, next one, next one. So like a multi-programming, the timer device interrupt after quantum time slice. 그냥 퀀텀은 잃어버리고 time slice. Maybe after 1 second, I call it interrupt. So I can go to the next process. So make sure no other process is left alone doing it. Anyway, this is also a bit beyond the course of the. 이것도 넘어갈게요. Personal computing system, your desktops, your laptops. Programmer is expensive. Salary of programmer expensive. Hardware cheap. 그죠? 요즘에 그렇죠? 물론 우리나라는 반대인가? 우리나라는 프로그래머가 칩이고 그래 우리나라는 아직 반대일 수도 있겠다. Programmer cheap, hardware expensive. 그죠? 하드웨어가 얼마나 칩하면 우리 저번 시간에 보지 않았어요? 클라우드 돈 빌려 쓰는 거 뭐 1시간에 얼마 달래? 1시간에 얼마 되지도 않았죠? 1,000원도 안 되잖아요. 그죠? 얼마나 싸면 사람들한테 그렇게 공짜로 뭐 버추얼 CPU 4개, 5개 막 붙어있는 것도 그렇게 싸게 죽었어요. 그렇죠? 그리고 뭐 사람이야 우리나라는 뭐 프로그래머 노동력 착취하니까 공짜로도 쓸 수 있는데 뭐 그렇죠? More of a other countries scenario. But simply means when you try to develop a software, the cost nowadays is most of the cost is on the human resources. 사실 소프트웨어 개발하는데 하드웨어도 싸면 비용 나갈 게 뭐밖에 없어. 사람밖에 없죠. 그죠? 요즘엔 사람 비용이 훨씬 커요. That's what they try to say. It's not very important, but. So and then it goes to a parallel system, multi-core process. 이것도 조금 어려운 얘기라 이 다음 거 하고 할게요. Parallel system 하면 뭐가 있을까? Parallel systems. 뭐 슈퍼컴퓨터 하는데 슈퍼컴퓨터가 뭐해? 왜 parallel system이래? 병렬이 뭐예요? 병렬이 뭐 하는 거예요? 몰라. 그 내가 체스 게임 하는 거 한번 설명했어요? 안 했어요? 여기 보면 one of the examples they say it's all looks like a supercomputer. It says climate modeling, earthquake simulations, genome analysis, protein folding, blah blah blah. 오 여기 또 있네. Nuclear fusion research. 그렇죠? 그 뉴스 보니까 북한 애들이 또 무슨 핵을 터뜨린다고 그러는데 걔네 왜 이렇게 터뜨려야 될까? 슈퍼컴퓨터가 없으니까 실험을 실제로 터뜨려봐서밖에 못해서 그런 걸지도 몰라요. 요즘에 핵실험하는 나라 그렇게 많지 않잖아요. 특별한 경우가 아닌 이유에는 왜? 슈퍼컴퓨터로 다 시뮬레이션하고 웬만큼 다 나오는데 슈퍼컴퓨터가 없으니까. 옛날에 그런 뉴스도 있지 않았어? 그 북한이 플레이스테이션 3 많이 사다가 슈퍼컴퓨터로 막 엮어서 썼다고 하는 얘기도 있었잖아요. 농담 아니야. PS3에 들어가는 칩이 얼마나 좋은 칩인데. 그거 웬만한 CPU보다 훨씬 좋은 GPU 막 이런 거라 그 숫자 계산하는 데는 엄청 좋아요. 그래픽 전용이라. 그래서 웬만한 들어가는 CPU보다 훨씬 좋을 거예요. 그거 막 엮어가지고 플레이스테이션 3 막 엮어갖고 시뮬레이션 해보려고 그랬는데 플레이스테이션도 못 사시는 분들이라 힘드셔서 못했다는 얘기도 있고. Anyway, 무슨 얘기 하려다 이렇게 왔냐? I mean blue jeans. When there is these supercomputers, we hear this a lot, but we're not so sure what they are being used for. So, well, it says a lot of huge computation that can do separate tasks at the same time. For example, how does Google sorting the keyword search of the entire world? 구글에 들어가면 구글이나 네이버 들어가면 그거 있지 왜? 현재 실시간 검색어 1등, 2등 그거 어떻게 해? 여러 사람이 동시에 엄청나게 많이 찍어대는데 그렇죠? 네이버는 그나마 우리나라지 구글은 전 세계 다 하잖아요. 그거 어떻게 해? Right? They need to do a sorting algorithm like we studied in our course. Right? They do a simultaneous sorting of a different data set and they bring it back together. Maybe supercomputer is better. For parallel computing is a better way of doing it. Or chess game that I wanted to mention. Chess 아니면 체스보다 좀 쉬운 거 뭐 있을까? 그래, 체스 하자. Chess is what? Start from the top. How many moves can you make in a chess game? How many moves can you make in the first move? 뭐 어떻게 생겼어? 체스 이렇게 생겼지. Player 1, player 2. 고스톱을 할까? 고스톱이 훨씬 낫려나? How many moves can you make? Well, I don't know how many 그 뭐냐 작은 애들 솔전가? 혼 뭐 이런 있잖아. I can move this one front, or I can move this one front, I can move this one first. So there are many options that I can do, right? Maybe that would be my choice. I decide if this tree means that I decide move this one first. Okay, this is move 1, move 2, move 3, move 4, move 5. After that, how many moves can I make? Could be also a lot of moves. And I take one move from that many different choices. But in order to win a chess against the other player, it would be nice that you can predict the moves of your opponent. 그죠? Imagine that if you try to combine that into this tape, in this tree, you will have crazy number of choices that you can explore. So this will be your problem space. This will be your problem space. And your algorithm will be trying to find the best path in this big picture. 체스로 하면 엄청날 거예요. 그렇죠? You try to do this in your computer in a one way only, one option only. Then it might be okay, but you're never gonna win. So what if the parallel processing they explore every single possibility. Process 1 is doing this one, this one, this one. They explore every single possibility. And then your opponent makes one move. You can take a look at all the possible moves and the next maybe 8 sequences. 그 체스 챔피언이 자기 머리로 몰라. 요즘에 체스 챔피언이죠. 세계 체스 챔피언이 자기 머리로 자기가 한 대여섯 개 앞까지는 본다고 그래요. 그죠? 이론상으로는 컴퓨터가 만약 그 사람이 5개 앞에 무브를 보면 야, 5개 무브 앞을 본다는 거는 얘가 이렇게 움직였을 때의 그 앞에 5개, 이렇게 움직였을 때 그 앞에 5개, 이렇게 움직였을 때 그 앞에 5개를 다 보니까 엄청나게 머리로 계산하고 있는 거잖아. 이론상으로는 컴퓨터가 앞으로 6개만 보면 이길 수 있는 거 아니야. 그죠? 그러니까 될 수 있는 모든 가능성을 병렬 처리로 다 해보는 거예요. 가능하죠? 그럴 때는 병렬 처리하는 게 훨씬 도움이 될 수도 있겠죠. 그죠? 물론 이제 하나의 예입니다. 이게 뭐 꼭 병렬 처리를 해야 된다 그런 얘기 아니라 IBM 이런 진 같은 거, 뭐 이런 IBM에서 나온 머신 같은 거, 그 한동안 뭐 체스 세계 챔피언이랑 컴퓨터랑 해서 이겼니 졌니 이런 얘기 많았죠. 그 몇 년 전부터는 아예 사람이 째바리가 안 돼요. 잘해야 무승부일 거예요 아마. 잘해야 무승부. 요즘엔 하지도 않을걸? 요즘엔 하지도 않을 거예요. 아니면 최근에 그런 것도 있었는데 신문에 나온 거 못 봤어요? 일본 애들이 물론 이거 약간 인공지능 쪽이긴 한데 그런 것도 있었어. 최근이 아니라 몇 달 전에 그 우리 수능 일본 애들도 수능 같이 있잖아요. 대학 들어가는 시험. 걔네 하나의 그 연구진의 목표가 몇 년 안에 우리로 치면 걔네 도쿄대니까 뭐 서울대, 연구대 이거를 컴퓨터가 시험을 쳐서 들어가게 하는 게 목표래요. 그래서 올해 그 컴퓨터가 시험을 봤어요. 대학 시험을 봤는데 도쿄대는 떨어지고 그 아래에 있는 데는 붙었대요. 무시무시하죠. 비슷해요. 이걸 똑같이 이 트리예요, 트리. 이만큼 많은 트리를 다 분석해갖고 답을 찝어내는 거예요. 약간 인공지능적인 게 들어가긴 하겠지만 인공지능이라는 게 별게 없어요. 생각할 수 있는 거 다 가지고 있다가 계산하면 땡이니까. 그래서 내후년쯤에는 자기네들이 가능할 것 같다고 신문에 나왔더라고요. Anyway, parallel computing systems. Brief introduction on that part. 그냥 한국말로 했어요, 그거는. 야, 중국 사람들이 만든 요즘에 슈퍼컴퓨터 1, 2등은 다 중국이 하지 아마? 그렇죠? Distribute processing also same as a similar idea for parallel processing, but simply put as distributed systems. 뭐 여러 가지가 많이 있는데 뭐 나눠서 하고 하는 것들, distributed systems, searching for extraterrestrials signals SETI at home like. 아니면 simple as your BitTorrent. BitTorrent is also distributed system too. You're getting a file from multiple users at the same time, different piece. So they just wanted to give you some introduction on this part. 뭐 있나? 이거 뭐 같아요? 그 누텔라라고 이렇게 얘기하면 모르고 그 P2P 다운받는 사람도 있잖아요. 그 그림으로 그려놓으면 이래요. 그림으로 그려놓으면 이렇게 돼요. 점 하나가 사람이에요. 그렇게 보면 아주 간단해요. 내가 이 사람한테 이렇게 다운을 받고 있고 이거 나중에 쭉 그려놓으면 그거랑 비슷하대요. 사람 머리 뇌세포 그려놓은 거야. 근데 뇌세포는 다 그릴 수가 없으니까. 이것도 마찬가지로 플래닛 랩이라는 분산화된 시스템들 이렇게 쫙 전 세계에 이렇게 뿌려졌어요. 우리나라에도 하나 있어요. 내가 알기론 대전에 하나 있는 걸로 알고 있어요. 저렇게 쓰면 여기 앉아서 남의 나라에 있는 컴퓨터에 요만큼에 들어갈 수 있어요. 아마 카이스트에 아마 하나 있을 거예요. 뭐 그냥 컴퓨터 조그만 거 하나예요. So you can build your own program and then you can distribute. You can give your program to other computers in other countries and then you can control them remotely. Then you can do a lot of testings on that part of it. 여러 가지가 있습니다. 이거 real-time systems. Sensors, actuators. actuator가 뭘까? actuator. 그 영화 같은데 아니야 영화. 그 자동차 공장 같은 데 막 이렇게 움직이는 무빙 암 이런 거 있죠. 이렇게 움직이는 애들. 부품 조립하고 막 돌아가고 컨베이어 벨트 돌아가고 그런 거 actuator라고 그래요. When you try to build a operating system to control such devices, those devices has to be precise on time. 그죠? 정확하게 0.01초에 움직여야 되는 애들이잖아. 그죠? Can you just use your your operating system on your desktop to control such devices? It's possible, but there will be delay. It will be delay. 아까 전같이 the example for scheduling example. Process 1 is asking to move. Process 2 asking to stop. Process 3 maybe do nothing. Maybe you you give a proprietary on each priority. Not proprietary. Priority each process. Maybe if someone says move, that's important operation. CPU must be doing that first. So real-time operating system is focused more on that part. So scheduling, in terms of scheduling algorithm, very precise, and there are higher priority processes to be executed. 이거 잘못하면 죽어요. Failure if responses are too long. Secondary storage are limited. 내가 한번 real-time 시스템 얘기해 준 적 있지 않아요? 없어요? 포스코 내가 얘기 안 해줬어요? 안 해줬어? 시간도 남는데 해줄게. 내가 학교 다닐 때 포스코랑도 프로젝트를 좀 했어. 한 1, 2년 했는데 거기도 이제 혹시 포항에 가본 사람 아니면 포항이나 광양이나 제철소 가본 사람 있어요? 견학 가봤어요? 그 뭐 어디 기억나요? 큰데 막 모자 쓰고 들어가서 걸어다니고 막 그죠? 막 철 왔다 갔다 하는 거 보여주고 쇠물 뽑는 데 막 보여주죠. 가면 공장 길이만 2, 3km예요. 한쪽으로 쫙 해갖고 그럼 거기에 저런 액추에이터라고 그래야 되나? 막 롤링이 쫙 가면서 쇳물 뽑아들이는 것부터 이렇게 눌리는 것까지 쫙 지나가요. 그럼 이게 막 돌아가면서 움직여야 되잖아요. 쇠는 또 무겁잖아요. 근데 가끔가다 이제 시스템이 좀 이상해지면 중간에 돌아가던 게 멈추거나 하면 얘네는 큰일 나요. 왜 큰일 날까? 물론 딴 데도 다 마찬가지긴 하지만 안 큰일 나는 데가 없긴 하지만 얘네는 진짜 큰일 나요. 왜냐하면 쇳물이 가다 멈추면 그냥 거기에 눌러 붙어요. 매체 온도가 그 벨트 위에. 그러면 저쪽에서 쇳물도 다 서야 되고 쇳물 끓이던 것도 끓이다 멈추면 다 붙잖아요. 그럼 뭐 다 버려야 되니까. 그리고 컨베이어 란트에 붙으니까 한 1, 2초만 한 몇 분만 서 있으면 거기 붙으면 다 드러내야 돼요. 드러낼 수가 없어요. 쇠를 다시 녹여서 드러낼 수가 없잖아. 그러니까 그런 거 제어를 많이 해요. 그래서 조금이라도 시그널이 늦으면 움직여라 할 때 안 움직이면 그냥 한 번 라인이 쓰면 며칠 동안 라인이 쓰고 걔네는 시간당 쓰면 몇십억이 날아가니까 돈이 날아가니까. 그래서 그런 거 못하게 하는, 그런 거 사전에 차단하게 하는 시스템 이런 것도 상당히 많이 해요. 그런 것도 있고 또 뭐 한동안 막 뭐 어디 무슨 이란에 있는 뭐 핵발전소가 뭐 해킹당했다 뭐 이런 얘기도 많았잖아. 그런데 들어가는 그 바이러스 뭐 이런 거 지금도 스톡스넷 뭐 이런 거 찾아보면 나오는데 거기 가면 저런 거 하드 리얼타임 시스템 소프트웨어에서 보내는 시그널이 뭐 그런데 하는 거는 밸브를 닫아라 열어라 뭐 이런 거란 말이야. 닫으면 뭐가 들어가고 안 열면 들어가고. 그런 바이러스들은 닫아라 하면 열고 열어라 하면 닫아요. 그러니까 뭐 폭발되게 만들고 막 그런 게 failure if responses are too slow or wrong, high sequence of very high consequences of a damage. 여러분들 뭐 쓰는 컴퓨터에서는 잘못하면 그냥 껐다 키면 되지 사람이 죽고 돈이 버리지 않잖아요. 이쪽엔 상당히 심각한 문제들이 많아요. Soft real-time system less accurate if response time is too long, useful in application multimedia virtual reality. 이건 완전히 hard real-time 시스템이고 뭐 제어를 한다는 하는 거고 뭐 그거보다 조금 덜한 애들은 이런 식으로 할 수 있다라고 하는 예제로 보면 돼요. Real-time operating systems too. 자, 여기까지만 하자 오늘. So we briefly look at for the supplementary part of the system software operating system part. 중간고사. Let me discuss briefly on your midterm exams.